This is one last brief lecture just to suggest to you how the Fourier series can be extended to the Fourier transform. So in the case of the Fourier transform, we don't assume that the function we're dealing with is periodic. So suppose we wish to, say, approximate a function f of t that is not periodic. Then we can do so over a finite interval, say from some minus t over 2 to plus t over 2. And just pretend that the function is periodic with period capital T. So in other words, we take the function itself over this interval, say from minus t over 2 to t over 2, and then we just extend it in such a way that we get a periodic function. Then we can take the Fourier series, assuming the resulting function's piecewise smooth. So we get a Fourier series with sinusoidal components at integer multiples of the fundamental frequency 2 pi over capital T. And let's say that we call this frequency increment then delta omega. So that's the difference in frequency between two successive components in the Fourier series. Then we can write our Fourier series as follows, using the complex form. It's n equals minus infinity to infinity Cn e to the j delta w n t. And we can rewrite this. It happens that we can rewrite this as 1 over 2 pi times the sum from n equals minus infinity to infinity of t Cn e to the j delta w times n times t. And now here I've multiplied by t over 2 pi, which is the inverse of delta w, so I'm going to multiply by delta w. So now, think about what happens as capital T goes to infinity. In other words, as we approximate a larger and larger segment of the domain of the function of f. This sum will, if you like, intuitively approach an integral. Think of this delta w, which is going to be tending to 0, think of it as a dt, and this sum of all these values over a vanishingly small increment of frequency as being an integral. So it behaves like the integral from minus infinity to infinity of f hat of omega times e to the j omega t dt, where f hat omega is what TCN approaches as t goes to infinity, which is namely just taking the expression for the Fourier series coefficients and converting it into an integral as capital T goes to infinity. We will get this with and we can replace the minus t over 2 to t over 2 as minus infinity to infinity. So here we've replaced the delta omega times n with omega. And because this frequency, and in fact the infinite sum once again becomes effectively an integral, just as the previous one did. Then we call this f hat of omega the Fourier transform of f of t. And we call our earlier integral the 1 over 2 pi times the integral from minus infinity to infinity of f hat of omega e to the j omega t d omega, the Fourier transform. This is the Fourier integral, the inversion integral, because we're going from f hat of omega to f of t. So this shows that what this integral does is express f of t as a sum of sinusoids. So it decomposes the signal f of t into a sum of sinusoids, or rather a weighted sum of sinusoids, where the weighting function is precisely the Fourier transform. So it looks quite a bit like the Laplace transform, except with S taking the form j omega. However, there are some technical differences, specifically in the notion of convergence that's used. The Fourier transform has similar properties to those of the Laplace transform. And like the Fourier series, it also satisfies Parseval's theorem. Or a new version of Parseval's theorem. For the Fourier transform, Parseval's theorem takes this form. If you take the integral of the power of f of t in the time domain, you get 1 over 2 pi times the integral of the modulus squared of the Fourier transform in the frequency domain. So intuitively, the power in the signal f of t is the sum of the powers of all of its sinusoidal components. Because here we're dealing with complex sinusoids, because we started out with the complex form of the Fourier series, we don't have the 1/2 that we have with real sinusoids. So this square of the modulus of f hat of omega represents, in fact, the power of the sinusoid with frequency omega, the sinusoidal component with frequency omega. So you can get the power that's expressed here in the time domain by adding the powers of all of the sinusoidal components, which is what this integral is doing. And then there is this factor of 1 over 2 pi as well that you have to take into account. So the Fourier transform is used, as I said before, and as the inversion integral shows, as a way of decomposing a signal into sinusoidal components at different frequencies from minus infinity to plus infinity, if you like. And just as in the case of the Fourier series for a real valued function, if f is real valued, you will have f hat of omega is the complex conjugate of f hat of minus omega. So in fact, it suffices to look at the Fourier transform for positive values of omega if you wish. Here's an example of a plot of the magnitude of the Fourier transform as a function of frequency. So this refers to Main's hum. So this is a hum, a sound, a vibration that you get from the wiring of a house, say. What they've done is used a microphone to record it, and they have computed the Fourier transform to show how the noise is spread out over different frequencies. So you see the frequency scale here, the logarithmic frequency scale, like the one we used for Bode plots. And we can see that this first peak occurs when the frequency, and I assume this is the frequency in hertz that we're looking at here, because this occurs at a value of 60. So we have a peak at 60, so it's as if the AC power is at 60 hertz, as it is here in North America. And this appears to be, well, it's not a perfect sinusoid because you can see a number of harmonics here. And as in our square wave example, for which we computed a Fourier series, we get harmonics only at odd multiples of the fundamental frequency of 60 hertz. Here's one that appears to be at 180 hertz, for instance, or 3 times the fundamental frequency. This one is at 300, 5 times. This one at 420, 7 times, and so forth. So presumably the waveform of the AC power in this example is not perfectly sinusoidal. It also contains harmonics. And that's perfectly normal. Anytime you take, we saw that when one of the special things about linear time invariant systems is that if you feed in a sinusoid at 60 hertz, the output is also a 60 hertz sinusoid. And it only changes in amplitude and phase. But every real system incorporates some nonlinearities. And like the rectifier examples that we looked at, when you feed a sinusoid into a nonlinear system, you get a component of the output at the frequency in general, at the frequency of that input signal, but also at harmonics. So in this case, instead of being perfectly sinusoidal, we have harmonics of the fundamental frequency. There's more to it than that. They're also picking up, let's say, a certain amount of noise, for want of a better term, which is why you see these other features as well in what we typically call the spectrum of the signal. If we take the Fourier transform, we call it the spectrum because it divides the signal up into orthogonal components at different frequencies. So this is a pictorial example of a Fourier transform, of the magnitude of a Fourier transform for this acoustic signal, which is the hum generated by, say, household wiring. If you think back to the beginning of the course, when we were looking at examples of differential equations, our last one was an example of a partial differential equation, which represented a vibrating string. And we in fact found an infinite number of solutions to that equation. One essentially corresponded to vibration at a fundamental frequency, where the string was in the shape of a half wave. The string that was fixed at its two ends was in the shape of a half wave. That gave us the fundamental frequency. And we also got other solutions at integer multiples of that frequency. So if we looked at the spectrum of a vibrating string, you would see something similar to this. You would see a spike at the fundamental frequency, and then at integer multiples of that fundamental frequency, you would see other spikes representing the harmonics. And then you would also have inevitably some noise, so you would see other features as well in the spectrum. And in fact, it's interesting to go back to that example of the vibrating string, because it's precisely because you get these infinite families of solutions when you're solving PDEs that the Fourier series was developed initially for the solution of partial differential equations. So, for instance, if you wanted to describe an arbitrary, piecewise smooth shape that the string might have, you could use a Fourier series to approximate such a shape. If you were, say, plucking the string in some funny way, so that it didn't start out with a perfectly sinusoidal shape, you could use a Fourier series to approximate that shape, because you would be exciting not only vibrations at the fundamental frequency, but vibrations at harmonics as well. Those of you who are musicians probably know that you can pluck or otherwise excite a string so that you don't get much vibration at the fundamental frequency and you only get harmonics, for instance. But the idea is that there is this countably infinite number of solutions. So because the PDE is linear, you can entertain linear combinations of any of that infinite number of solutions. And that was what led to the idea of a Fourier series, which is simply a linear combination of an infinite number of sinusoids. So if you continue on and you do other related courses, obviously you'll do SE 380, where you probably won't do any real Fourier analysis, either Fourier series or Fourier transforms. But if you take a course in scientific computation of any kind, then the Fourier transform will probably be you'll find is a staple topic. Here we've shown how the continuous Fourier transform arises, but if you want to compute a Fourier transform using a digital computer, you're going to compute a discretized version, a sampled version of this Fourier transform. So a sampled version, where you're sampling at regular frequency intervals, not in the time domain but in frequency, that is called a discrete Fourier transform. Obviously, they're of importance for scientific computing because we use these discrete Fourier transforms precisely in order to be able to compute things with a digital computer. And a well-known efficient algorithm for computing the discrete Fourier transform is called the fast Fourier transform. So the fast Fourier transform, or FFT, is not another transform, but rather an algorithm for computing a discrete Fourier transform. So if you go on to take any courses on scientific computing, this will be an important topic that will be covered. Let's wrap things up there now. This has been the third in a series of relatively short video lectures that have just sort of helped to tie up some loose ends and maybe give a little additional perspective to the course. And with this, we conclude the course lectures.